All right, let's get started. This is class 5. It's called the experiment. Oh, yes, because we're going to hit on the experiment. Now, Jeremy, I don't know if you had time to go over class 3, but it's okay. I'm going to do a recap, okay? So in class 3, if you remember, we ended with Einstein and the photoelectric effect. So Einstein broke down how, you know how light's a wave, right? Those two walls. And you've heard of a photon, right? Photon is actually a particle of light. So now Einstein established that light is also a particle. So now they don't know what light is. Is it a particle? Particle means it's a little piece of matter, it won't go through the wall. Or is it a wave, like light? And then last class, class 4, we ended with talking about the electrons. The electrons going around the atom. And Bohr finally established the fact why atoms don't fall into the nucleus, or electrons don't fall in the nucleus. But we have no explanation as to why 2 atoms are in the first shell, 8 atoms are in the next shell. Where do you get these magic numbers from, Hey, Dom, if you need my phone to entertain... Oh, you got the iPad. Oh. So that's kind of where we left off. And I was going to follow through with the carbon-14 thing, but we're going to hold off on that because I just want to jump into this, So we will go to Louis... Now, I have no idea how to say this. He's French. Louis de Broglie?
Broglie.
In French?
Yes.
Oh. Okay.
Broglie.
And actually he was a prince, so it's Prince Louis. So he was a physicist who happened to be a prince in France. Now, not all the aristocracy were dummies. Louis was a grad student who, like Einstein, shared a feeling that there was a deep meaning in the dual nature of light. So all the scientists are wrestling with what is light? Can it be this and that? Most scientists are like, this doesn't make any sense. He was really wrestling with it. Like, what does it mean? Like, how does this really affect our world? The fact that light can be a particle and it can also be a wave, which we know it is. So he came up with a really simple chart. So he's like, look, Einstein proved that light is a particle, but we also know that light is a wave. Okay, what about matter? Now, everyone knows matter is a particle. That's the whole point of matter. Everything is made up of little pieces of something, pieces of matter. But he's like, well, if light can be a particle and a wave, might matter also be a particle and a wave? He wondered, why might there be some symmetry in nature? If light was either a wave or a particle, might matter also be a wave or a particle? So he wrote a simple expression for the wavelength of a particle of matter. Essentially, he proposed the idea that all matter displays a wave-particle duality. So usually you hear the wave-particle duality of light, because light's much easier to talk about. So in school, they never talk about the wave-particle duality of matter, because then you would have to start talking about quantum mechanics, and people don't want to get into that. His great achievement was to take the idea of the wave-particle duality and carry it through mathematically, describing how matter waves ought to behave and suggesting ways in which they might be discovered. So in his thesis, remember, he's a master's student trying to get his doctorate, so he's writing his thesis. He started out from the 2 equations that Einstein had derived for light quantum. And I think I wrote them up there, I didn't really stress them, but it's E equals hv. So energy equals Planck's constant times, it's not V, it's actually the Greek letter nu, and that stands for frequency. And P, which is momentum, equals Planck's constant times V nu, divided by C, the speed of light. Don't really need that, but if you want to write it down, So he argued that the failure of experiments to settle once and for all whether light is a wave or a particle must therefore be because there are 2 kinds of behavior are inextricably tangled. So he was like, look, nobody can figure out what light is, because if you try to run an experiment showing that light's a wave, well, that's easy. But if you try to show an experiment that light's a particle, then you show it's a particle. And everybody was confused. He's like, the reason why we're confused is because we're misunderstanding not just light, but matter. These things are tied together. To measure the particle property of momentum, you have to know the wave property called frequency. So P equals h over lambda. So the first test of this formula came as Broglie. I'm just going to say Broglie, because that's what I've been saying. So I don't know if that's wrong. If you're watching this online, I apologize in advance. If the electron in the hydrogen atom were a compact particle, how could it possibly know the size of the orbit it should move in? This is what we talked about with the atom, remember? How does the second orbit of the atom know that it only holds 8? And that's it. After 8, you got to jump to the next orbital shell. In addition, how could each orbit know when it was full, and why would it fill up in such increments? Why these whole numbers, 2, 8, 16, 32? Planets hold different orbits due to gravity, but what was happening at the quantum level? You see, electrons were thought at the time to be good, well-behaved particles, except for the curious way they occupied distinct energy levels inside an atom. De Broglie realized that the fact that electrons only existed in orbits defined by whole numbers, or integers. Remember, we take for granted, because we're not hardcore scientists, that the way atoms work, orbit 1 and 2, and these whole numbers, there's nothing really like it in nature. Nature isn't full of... think about length. There's nothing distinct about length. Length could be whatever you want. You define it, it's in pieces. But these things were distinct, like 2. Not 2.2 or 2.06543. It's just 2. Or it's just 8. So he realized that these integers also looked in some ways like a wave property. He said the only phenomena involving integers in physics, wow, I can't talk, in physics, were those of interference and of normal modes of vibration. This fact suggested to me the idea that electrons, too, could not be regarded as corpuscles, which is what Newton called them, but that periodicity must be assigned to them. Well, what does that mean? He played the violin. He was also a musician, which actually Einstein also played the violin. A lot of physicists played instruments, which I find interesting, because when I studied about chemists, they don't play instruments. I don't know what that means. He was an amateur musician as well, and he noticed the similarities in music. Normal modes of vibration are simply the vibrations that make the notes of a violin string or sound wave in an organ pipe or guitar or any string instrument. In other words, harmonics. A harmonic of a wave is defined as a component frequency of a signal that is an integer multiple of the fundamental frequency. And the rest of that, you can just read it. It's very technical, but here's the gist of it. This is how strings instruments work. Like your guitar string, you have different length strings. And you know when you put your little finger on the pick, you're pointing, and now if you do it right in the middle, that's a half harmonic, and you have 2 wavelengths. If you pinch the other 2, you see you have thirds. These are chords. These are the chords, and you can see them right here. But you can see on one line, depending on what type of frequency or vibration wave you have, if you were to, like that guitar string, when you hold it and you pluck that note, the reason why you make that note is because you can only, that length of string only has so many of these vibrations through it. They fit exactly. That was the analogy he was coming up with. So what struck him so acutely is that some waves with certain frequencies fit the string. He's talking about an instrument. This is very similar to the way electrons fit into atom states, corresponding with quantum energy levels, as in 1, 2, 3, 4. Instead of straight, stretched out string, so now take your guitar string, however you imagine it, and now curve it into a circle, like an orbit around an atom. A standing vibration wave can run happily around the string, provided the length of the string is a whole number of wavelengths. Once the string had a specified amount of wavelengths, then no more will fit. This gave a rather simple explanation as to why each orbit would only hold a certain amount of electrons. So just like the chord on a guitar, that when it holds only, let's say it holds 8 vibrations. That's how it makes that note. Now you take that and you stretch it around, and you say, okay, electrons have a wave frequency that's a certain size. It would make sense that only 8 of them could maybe fit in that going around. And that you can't fit more than 8 because there's no more room. His examiners liked the math, but they did not believe that it had any physical meaning. They regarded it as a simple quirk of mathematics that linked particles with waves. And here's an image. So you can imagine the wave going around. So now the electron's a wave. And one wave, obviously, you got room, 2, 3. But now you can start to see how an orbit can actually fill up if you imagine it as waves. So he thought further. The length of a violin string required to produce a given pitch are determined by the number of half wavelengths of the vibration that fit along the length of a string. So similarly, with the electron as a wave, the allowed orbits might be determined by the number of electron wavelengths that fit around an orbit's circumference. So he was relating harmonics and instruments now with physics and electrons because it works. He's just using his own observations. Experimentally, de Broglie knew the right wavelengths to look for since Einstein's combined equations have the simple relation. So if you take Einstein's combined equations for the wave-particle duality of light and actually Planck's, and you combine them together, you get P, momentum, is equal to H, Planck's constant, times frequency. Frequency is a wave, divided by C. So everything is now related just using mathematics. Since wavelength is related to frequency by lambda, and I was going to write it out, but I didn't have time. Lambda is the little upside down y. Lambda is equal to the speed of light divided by frequency, meaning your momentum times your frequency equals h. Or in other words, momentum multiplied by wavelength gives Planck's constant. So everything is just lining up mathematically, everything's lining up visually. The smaller the wavelength, the bigger the momentum of the corresponding particle, making electrons with their small mass and correspondingly small momentum the most wave-like of all particles. So using the mathematics, the larger and larger something is, the less and less wave-like it is, which we know. Like there's nothing wave-like about the wall, you know? But mathematically, the smaller and smaller, the closer you get to that h, that unit that you can't go any smaller from, the more wave-like it appears mathematically. Now, we don't know how seriously he took this conjecture, though we do know he certainly didn't recognize it as advancing a revolutionary view of the world. And here's a really cool quote I found where he says, "He who puts forward the fundamental ideas of the new doctrine often fails to realize at the outset all the consequences. Guided by his personal intuitions, constrained by the internal force of mathematical analogies, he is carried away, almost in spite of himself, into a path of whose final destination he himself is ignorant." So when he started this, he had no idea that he was going to change the world. He's just like, look, these are my basic observations. In layman's terms, he had no idea how this would change the view of the world. See, that's the problem with writing your own slides. Is everything I say, I end up writing down. De Broglie took his speculation to his thesis advisor, Paul Leeuwenhoek, famous for his work on magnetism. So here's his paper. He writes it all up. Looks good. He takes this to his advisor because he's trying to get his PhD and get into the field. And obviously he's probably going to look at him a little cross-eyed. He was not impressed. He noted that in deriving Bohr's formula, de Broglie merely replaced one ad hoc assumption with another. Remember, Bohr was under a lot of scrutiny because he couldn't explain what he was doing. He was just making up rules. I don't know why 8 fit, they just do, And you saw the periodic table, you saw how things lined up, I tried to explain it, but he couldn't come up with a mathematical way of doing it. So physicists they were impressed, but not too impressed, because they're like, look, we need a fundamental foundation for why this is working. So now you're coming up with something, again, you're just extrapolating, but you're just coming up with one assumption to explain another assumption. Moreover, de Broglie's assumption that electrons could be waves seems ridiculous. How can matter be a wave? Were de Broglie an ordinary grad student, Leeuwenhoek might have similarly dismissed his ideas. But since he was Prince Louis, apparently the French didn't cut all their heads off. There's some aristocracy left. Aristocracy was meaningful even in the French Republic. So no doubt to cover himself, Leeuwenhoek asked for a comment on de Broglie's idea from the world's most eminent physicist, Albert Einstein. So he sent a telegraph to Albert Einstein, look, what do you think of this? Because if you think this is stupid, then I'm going to dismiss it and call it a day, This is what Einstein said. Really interesting quote. "This young man has lifted a corner of the veil that shrouds the old one." Basically, again, Einstein, there are so many biographies on him, he doesn't believe in God, but when it comes to physics and all his quotes, he's always talking about God. But it's not as simple as Einstein thought of science as God. He was sort of like an agnostic theist, Meanwhile, there was a minor accident in the laboratories of the telephone company in New York, which would lead once again to an accidental discovery supporting quantum mechanics. Clinton Davidson was experimenting with the scattering of electrons from metal surfaces. And here he is. While Davidson's interests were largely scientific, the phone company, which was Bell Labs, which would later eventually become AT&T, was developing vacuum tube amplifiers for telephone transmissions. And for that, the behavior of electrons striking metal was important. So they were developing vacuum tubes, and they were electrons, because obviously electricity for the lines. And so they were really interested on how electricity and how electrons, in this case, were responding in these vacuum tubes. Electrons usually bounced off the normally amorphous metal surface in all directions. So electrons hitting a smooth, consistent surface are going all over the place. Their experiments were to figure out how can we tame this and how could we get better results without getting interference. The experiment was to minimize that. But there was an accident in which air leaked into the vacuum system and oxidized the nickel surface. So Davidson, in order to fix it, he heated the metal to drive off the oxygen. By heating it, the nickel crystallized, essentially forming an array of slits. To put it in layman's terms, the scientists were experimenting with the scattering of electrons on a smooth surface. So through a series of accidental events, just happenstance, they changed the smooth surface to crystallized edges. Imagine like I don't know, pieces of metal sticking up like this, kind of like a Venetian blind type thing. A surface perfect for showcasing the wave nature of atoms. So now, electrons bounced off in only a few well-defined directions instead of all directions. So before they were bouncing all over the place. After he heated it and ended up creating a surface he had no idea he did, now he went back to studying it, and instead of electrons going all over the place, they were only going in certain directions. Well, turns out he was seeing an interference pattern. Remember, we talked about the interference pattern with the double slit experiment, demonstrating the electron's wave nature. This discovery confirmed de Broglie's speculation that material objects could also be waves. So this is happening simultaneously. Like, the same time, this is in France, and now you're in America at a phone company. And as soon as he postulates this, he ends up seeing these other American experimenters like, whoa, I think we're seeing what you're seeing. Like, your conjecture makes sense. So to sum it up, by 1923, physicists were for the first time forced to accept a wave-particle duality. Now, when I say forced, that's mean a little bit much. They were at least forced to think about it. You know, this wasn't quite fully accepted yet. A photon, an electron, an atom, a molecule, in principle, any object can be either compact or widely spread out. So you could show an object to be either bigger than a loaf of bread or smaller than an atom. You could choose which of these two contradictory features to demonstrate. The physical reality of an object depends on how you choose to look at it. So just like light, now we're seeing, just with an electron. Now granted, the electron is the smallest piece, well, not the smallest, but a very, very small piece of what makes our world. The fact that we could have that behave like a wave of light now calls everything into question. Physics had essentially encountered consciousness, but it had not realized it. And here's an interesting historical note. It's funny to know that in 1906, J.J. Thomson received the Nobel Prize for proving that electrons were particles. And in 1937, his son won the Nobel Prize for proving electrons were waves. Both father and son were correct, and both awards are fully merited, which I think I mentioned earlier, but threw it in. So from 1928 onwards, Broglie's wave-particle duality became overwhelming. So more and more they were doing experiments, and more they proved in small ways that this was true. Other particles, including the proton and neutron, were subsequently found to possess wave properties. The complete break with classical physics comes with the realization that not just photons and electrons, but all particles and all waves are in fact a mixture of wave and particle. So, if you remember in class 3, the whole point of them studying this is they were trying to figure out which is true. You know, they want to know how waves came from particles. And they were hoping that they'd find an answer, but now all they're finding is the fact that both of them they coexist, which doesn't make, it makes sense in some ways, but in other ways we know that matter can't be wavy, you know. It just so happens that in our everyday world, the particle component overwhelmingly dominates the mixture in the case of, say, a bowling ball or a house. So the wave aspect is still there in accordance with the relation P lambda equals H, although it is totally insignificant. So this desk has a wave property, but it's so insignificant because of its size that it goes out, and we'll go into that later when we get to Richard Freeman in the 60s, and he comes up with some really great analogies to make sense of that. So in the world of the very small, where particle and wave aspects of reality are equally significant, things do not behave in any way that we can understand them from our experience of the everyday world. Now, another really famous physicist, Arthur Eddington, he summed up the situation best in his 1929 book, The Nature of the Physical World. This is a really good book. They had it on Amazon, but it was sold out or whatever. But it's written in 1929, but I swear it reads like today, as far as it doesn't feel old. But here's a quote. "No familiar conceptions can be woven around the electrons. Our best description of the atom boils down to something unknown is doing we don't know what." And that's basically where we're at now. We have not progressed. We've understand more fully that something unknown is going on that we don't know what. So now we come to Schrödinger. Of course, here's where the cat comes from. Now, Erwin Schrödinger, like all geniuses, he was a quirky fellow. This guy he was funny. He was a womanizer. He actually developed all his equations. He birthed quantum theory while going on vacation with his mistress on an island, way out on the coast of Denmark. And his wife was okay with this. Europeans are weird. Now we forget all these great minds in science. We forget all these great minds are scientists and thus people. So their motivations can be strange sometimes at best. Schrödinger had a major problem with Bohr's atomic model. Yes, it worked. Yes, everyone had accepted it. But this is a quote, so don't get mad at me for my language, but I have to say it. Those damn quantum jumps drove him mad. If you remember when we talked about it, remember I explained how on an atom, the electron just doesn't, here's orbit 1, and you move to orbit 2. There's no in between, to do track, you have here, and you got the 10-yard line. There's no 1 yard, 2 yard, 3 yard. It doesn't exist. It's either 1 or 10. You just jump. Schrödinger, again, he was old school. He was classical. Classical physics meaning he wanted things to make sense. You can't just jump. And he hated those damn quantum jumps. So like Einstein, he didn't fall into the camp of physics just describing our world. He wanted to explain it. And having electrons magically jump levels not only didn't make scientific sense, it doesn't seem to fit with reason. There's nothing reasonable about jumping from here to the 10-yard line without existing any space in between. Schrödinger was very outspoken. He really spoke his mind. He told Bohr, "You surely must understand, Bohr, that the whole idea of quantum jumps necessarily leads to nonsense." So it is claimed that the electron in a stationary state of an atom first revolves periodically in some sort of orbit without radiating. Radiating means it puts out energy. There's no explanation of why it should not radiate. According to Maxwell's theory, it must radiate. So remember Maxwell, his brilliant equations that changed the world. They're what gave us electricity, all our technology, all the way up to 1920s, are derived from these equations, breakthrough work. According to his theories, electrons should radiate energy, and they should fall down, but they don't. So he was like, you're missing something. When an electron jumps from this orbit to another, from this orbit to another one, and there, I don't know what I was talking about. Does this transition happen gradually or suddenly? And what laws determine its motion in a jump? So Schrödinger's like, look, Bohr, if you want to say that I just jump from here to there, what are the rules? What's the criteria? How do you decide when to jump? What pushes you to jump? How do you get there? The whole idea of quantum, and this is another quote he said, the whole idea of quantum jumps must simply be nonsense. So he's clowning on Bohr, but Bohr's a big boy. Now Schrödinger wasn't looking to resolve the wave-particle paradox, but he saw Broglie's matter waves as a way to resolve the issue of these jumps. So Schrödinger jumps in to tackling the problem of waves and particles. But his motivation has nothing to do with trying to make sense of the world. He just wants to get rid of the jumping. So he figures if you think of them as waves, just like a string or a vibration, you could vibrate up, Then you're not jumping. You're changing vibrational modes, That made more sense to him. He credits Einstein's deep remarks regarding Brogile's findings as inspiration to first look at his ideas seriously. Again, even when Einstein's not changing the world, he's changing the world. Like all he has to do is like, that's interesting. And everyone, Einstein says it's interesting, Nobody would have even paid attention to Brogile and his waves. I mean, eventually, maybe a decade. But the fact that Einstein says, hey, you know what, this kid's onto something. Schrodinger's like, well, I'm gonna jump into it, Schrödinger, above all, wanted to have a description of a world that had electrons behaving reasonably. Schrödinger would thus seek to find a new universal law of motion. From a wave's initial shape, a wave equation predicts the wave's shape at any later time. Now, as you can imagine, waves or ripples in a pond, they have mathematics that describes all that, When you watch Finding Nemo or you watch any animation, they call it fluid dynamics, They don't animate the water, Nemo comes up and the water's all rippling around him, the boat. They don't animate that at all. They all just have wave equations, physics. Game designers, my brother-in-law went to game design school, and they actually call it a physics engine. That's what it is. That's the driving force in your PlayStation and your Xbox One is the graphics card does physics, does calculations. It does Newtonian physics. It does wave mechanics. So when you're shooting people and they realistically, blood spatters out, that blood is a fluid. It behaves just like a fluid, a wave, a dynamic. It describes how ripples spread from the spot where a tossed pebble hits the water. An example, like digital water. Imagine if you had one of those digital water screensavers, you have them on the Galaxy phone, where you touch it and it ripples. Now those aren't real waves, right? But they're a wave function. The same mathematics we use to when we skip a rock in a pond to mathematically calculate those waves is the same thing we do when you mess with the screen. But now you obviously are applying it to your screensaver. So there's a problem. The wave equation that works for waves in water and also waves for light and sound doesn't work for matter waves in the same manner. Waves of light and sound move at a single speed determined by the medium in which the wave propagates. So sound, for example, sound's a wave. It can only move as fast as the medium. Its medium is air. It moves at about 330 meters per second, or 650 miles per hour. Light and water moves at 1/4 the speed, as it does in a vacuum. So light does not travel 186, whatever it is, 1,000 miles, whatever. It's 1/4 of that, which is still obscenely fast, and you can never measure it. But things change speed in what medium it is. The wave equations for matter, they can't do this. They had to allow matter waves to move at any speed through any medium. So for matter waves to work properly, because water's matter, they would have to move at the same speed in water as they would in a vacuum in space. They'd have to move the same speed in the air. They'd have to use the same speed in a big pile of jello, And this was a major issue because this isn't how the traditional mechanics work. In 4 papers he published within the next 6 months, Schrödinger laid down the basis of modern quantum mechanics with a whole set of equations describing waves of matter. This was groundbreaking. This was on par at the time with Newton. The work was immediately recognized as a triumph. Einstein said it sprang from true genius. Planck called it epoch-making. So it's dude, this is beyond anything amazing. Schrödinger himself was delighted to think that he'd gotten rid of the quantum jumping. That's all he cared about. His whole thing was, I just want to get rid of the jumping. Yes, I changed the world or whatever, but that's all he's concerned about. Almost simultaneously with Schrödinger's discovery, Bohr's postdoc student, so now Bohr's a doctorate. Now there's this new guy. Many of you who are watching Breaking Bad have heard of him. Werner Heisenberg. He presented his own version of quantum mechanics. So simultaneously, that Schrödinger just revolutionized the world, rewriting. Remember, he rewrote all of what we understood about physics, like Newton, according to waves. So it's a good thing that we didn't say, you remember I said before we call them Newton's laws because they're always true? Well, it turns out they aren't laws, you know. They are technically incorrect, you know, down to the billionth of a billionth of a billionth of a meter. But a waves, the way he described nature, it worked all the way from what we see in the real world all the way down to the atomic level. So Heisenberg worked together with Pascual Jordan and Born. He developed the beginning of what is known as matrix mechanics. And there's Heisenberg. They discovered the relation PQ minus QP equals H over I. So P is momentum, and Q, it gets complex. It's a quantum variable thing, you know. I'm not even sure why I wrote that equation. I thought it'd be cool, you know. The equivalent in the quantum world of momentum and position. I think that's what it is. P is momentum, Q I think is its position. Planck's constant appears in the new equation along with I. It's used a lot in mathematics. It's the square root of -1. Why that is there's certain constants and certain things that show up a lot in mathematics. There's another one which I didn't write, but usually if you go online, you'll see a lot the H, Planck's constant, with a little like line through it. It's called the reduced Planck's constant, and it's Planck's constant divided by 2 pi, because waves, sine, cosine, all that. So a lot of times you're dividing by 2 pi, yada, 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 so they just rewrite it that way. They stress that this is the fundamental quantum mechanical relation. Okay, but what does it mean? Explain it to normal people. Planck's constant was very familiar at this point. Physicists knew about the equations involving I, since such equations generally involve oscillations or waves. However, matrices were unfamiliar to most mathematicians and physicists in 1925, and the non-commutative nature of matrices seemed strange. Any of you guys go high enough in mathematics to cover matrices? Anybody? Yeah, you did, okay. One of the crazy things about matrices is they're non-commutative. I don't know if you remember the commutative properties and all that. Basically means that 5 times 3 is not equal to 3 times 5. Like the order definitely matters. 3 plus 5 is not equal to 5 plus 3. Now these are like really bizarre, but when you start doing matrices, and usually they're 2-dimensional, you can have three-dimensional, or it gets crazy, but these concepts weren't very well known. The mathematics has been actually around for over 100 years, but it was very obscure. The equations of Newtonian mechanics were replaced by similar equations involving matrices. Heisenberg states, in other words, matrix mechanics included Newtonian mechanics within itself, just as Einstein's relativistic equations included Newtonian mechanics as a special case. So he, just like Schrödinger, found a mathematical description that superseded Newton. Everything Newton said, all the physics in the past couple hundred years were encapsulated, but this was bigger. It took into account all the way down to the atomic. It was a strange experience to find that many of the old results of Newtonian mechanics, like conservation of energy, could be derived also in the new scheme. So he's doing this crazy mathematics, and while he's doing it, he's coming up with laws of conservation of mass, entropy. He's rewriting or redoing everything that they knew, but in a different way, in a way that would apply to small things. So once again, unfortunately, few people can understand the mathematics, and it was not immediately appreciated by most physicists just how significant his breakthrough Heisenberg and his group had made. Now there was one exception. There was one guy who got it. And sadly, most of us don't know who he is, but he's another super genius, Paul Dirac. Have you ever heard of him? I may be saying his name wrong too. Only a few months younger than Heisenberg, he was generally regarded as the only English theorist who could rank with Newton. He developed the most complete form of what we now call quantum mechanics. Or actually, I wrote that wrong. It should be called quantum algebra. So he created another type of mathematics, a mathematical scheme, that would end up doing the same thing. As a postdoc student, by a series of events, he managed to get a hold of Heisenberg's unpublished and unfinished work in progress. Heisenberg was attempting to fudge around with the non-commutative properties of matrices. But Dirac, he immediately saw the power in this property, meaning, remember, 5 times 3 is not the same as 3 times 5. He appreciated the fundamental importance of the simple fact that A times B is not equal to B times A. You see, unlike Heisenberg, Dirac already knew about the mathematical quantities that behaved in this fashion, and within a few weeks he was able to rework Heisenberg's equations in terms of a branch of mathematics developed by William Hamilton a century earlier. So there's a branch of mathematics that was over 100 years old. So now we're talking 1820. Totally had died out. Everyone forgot about it. And he rehashed it. And here's the ironic thing. The Hamiltonian equations were developed as an aid to the calculation of orbits of bodies in a system like the solar system, where there were several interacting planets. Now, Dirac discovered, independently of the Heisenberg group and independently of the Schrödinger, well, it shouldn't be the Schrödinger group because it's just Schrödinger, and the equations of quantum mechanics have the same mathematical structure as the equations in classical mechanics, and that they are included as a special case. So he does the same thing in a different way again, 3 times. Now, why am I stressing this? Because I stress how amazing it was that Maxwell was able to mathematically show that light was a wave. That was huge. Because remember, math is math. 5 plus 5 is 10. Like, there's no arguing. 5 plus 5 is still going to equal 10. When you start being able to prove things mathematically, it becomes a lot more real. Now, it's important because this type of stuff we're talking about is so crazy. For me, it would give me peace of mind knowing that there was some math behind it. But now I'm telling you there's math in 3 different directions that proves it. So he formed yet another way of expressing the dynamics mathematic using a special form of algebra he called quantum algebra, involving the addition and multiplication of quantum variables or Q numbers. So his algebra focused on the P's and the Q's. So I would say that mine, your P's and Q's had the root here. But I saw a thing on TV and they were saying the P's and Q's came from somewhere else. I don't know, These Q numbers are strange because in the mathematical model, it was impossible to say which of the 2 numbers, A or B, is bigger. In fact, in this system of algebra, one number being bigger than another number had no place. One thing couldn't be bigger than another thing, which was totally bizarre. But the rules of this mathematics fitted with what we observe, the particles, the behavior of atoms. So indeed, it is correct to state that the quantum algebra included matrix mechanics within itself. So Heisenberg creates this really abstract matrix mechanics that includes everything else within it. And then Paul Dirac comes up with another form of mathematics that includes within it the matrix mechanics, which includes within it everything that we know about physics. In a totally, completely different direction. However, his math did much more. Heisenberg was generous in his praise after reading Dirac's work. And this I find really especially interesting because you think scientists, a lot of times when I study like the history, scientists get petty, they don't want other people to get famous over them. And you think he'd be like, oh, who's this guy? He's coming out of nowhere. But this is what Heisenberg said. I have read your extraordinarily beautiful paper on quantum mechanics with the greatest interest. And there could be no doubt that all your results are correct. The paper is really, meaning his paper, Dirac's, is really better written and more concentrated than our attempts here. So Heisenberg was really humble about it. He's like, look, you nailed it, and you did it much better than what we were doing. So now you have these competing views. Both these mathematical models were extremely abstract. It denied any pictorial description of what was going on. So the matrix mechanics, this was mathematics so difficult that even the mathematicians at the time didn't know what was going on. And then Dirac comes up with a form of algebra that just, not only was it difficult, but it made no sense. How could you not have things be greater than other things? It was just bizarre. But it fit with what we saw in the real world. But both of them denied any picture of what was happening. And remember, we're humans. We like pictures. If we can't visualize something, it's very hard to learn something. That's my number one technique when I learn something is I have to visualize it. When I say pictorial, I mean waves. Schrödinger, he was really critical of Heisenberg. He hated Heisenberg's. And this is why. He says, I was discouraged, if not repelled, by what appeared to me a rather difficult method of transcendental algebra to find any visualization. Basically, he's like, look, I don't get what's going on. Remember, these are geniuses telling other geniuses, I don't know what you're talking about, But the biggest thing is, there's no visualization. What are you talking about? It's too abstract. Heisenberg was equally unimpressed with Schrödinger's wave picture. In a letter to a colleague, he wrote, the more I ponder the physical part of Schrödinger's theory, the more disgusting it appears to me. So Heisenberg was repelled by the fact that he was describing atoms like waves, just like waves in a pond. And there's a really important point in that disgust, which we'll see in a bit. So for a while, it seemed that there's two intrinsically different theories explain two different phenomena. But within a few months, Schrödinger proved that Heisenberg and Dirac's theory were logically identical to his own, just a different mathematical representation. So eventually they worked out, because at first they all thought they were saying different things. But they really, somebody had to spend the time and do the long division, and they realized they were all saying the same thing in a different way. So the more mathematically tractable Schrödinger version is almost universally used today. Schrödinger's wave equations are the ones you always hear about. They're the ones that throw people off, and they're the ones we're going to cover. But the other two, Dirac's and Heisenberg, give a much more accurate, but you have to be a genius mathematician to really comprehend them. So what does this all mean? Here are three separate brilliant physicists all come to the same conclusions in three different mathematically unique ways. So the only analogy I can come up with is in chess. You can represent the same move by explaining it plainly, saying, I'm going to move my knight over here, Or you can say king's pawn to king's pawn 4. Or you can use the most tractable notion as, d2 to d4. You're saying the same thing three different ways, but it's the same thing. It's how you're explaining the move. The different formulations of quantum mechanics are like this. Dirac's quantum algebra is the most elegant and beautiful in the mathematical sense, but it's very difficult to understand. The matrix methods developed by Born and Heisenberg and his collaborators are more clumsy, but nonetheless effective. Schrödinger's equations are familiar. We all know what waves are. We've all seen waves in the water and everything. They are known, they're tested, and they're easy for us to visualize, and that's why they are the most widely used. Schrödinger had, in an easy-to-understand way, rewritten Newton's laws so that they not only apply to large objects, but to the microscopic objects as well. Newton's laws, as it turns out, are merely approximations, which I already covered. Now that being said, they were approximate down to the billionth degree, so for all practical purposes they worked perfectly for the worlds of the large, but for the nanoscopic, or even smaller, atoms are beyond nano, they're femto, they were rendered useless. Now they were all encompassed. So these waves, you can actually mathematically describe like a catapult launching a rock using waves. Now that's way overkill. Why would you do that? Use Newton's laws are much simpler. And for all intents and purposes, they do the same thing. Schrödinger's equation thus governed not only the behavior of electrons and atoms, but also the behavior of everything made of atoms. Molecules, baseballs, planets. The Schrödinger equation tells us what the wave function will be in a given situation and how it will change with time. This is the new universal law of motion. He was able to use waves to duplicate Bohr's model and thus reproduce all the results he got for given energies of hydrogen. So now he's able to go back, and Bohr had pieced it together with duct tape. He was able to clean it all up and show mathematically how it all works. With waves, you can describe why 8 electrons fit in a particular orbit. Now, I don't know if you guys remember when I covered the atoms that I stated that those rules only work for the first 18. Remember I showed you some atoms where it skips to the next energy level? But we'll go over that later. That has to do with spin, what they call it. So he cracked the puzzle. We're good. What the heck is that? Wrong! Oh, shoot. I accidentally deleted a whole slide. Really? Hold on one second. I can't go back now. Shoot. What I was going to say is, at this point, you think the whole world will rejoice, right? Schrödinger had rewritten all the laws of physics by showing that particles can be waves. But the fact is, nobody rejoiced. Why? Because how can a particle be a wave? Like, what is it? Like, my phone is solid. I'm telling you that in the smallest level, every little piece of my phone is also a wave that can travel through the wall. But we all know, I don't care how many times you throw the phone at the wall, it's not going to go through it. And so this was a big issue because even though he answered a huge question, he just opened up more questions. And when they asked Schrödinger about it, he was like, I don't care. I just want to deal with the jumping. Now I know how you go from the 0-yard line to the 10-yard line. You vibrate. You vibrate forward, you know. But he also stated that, again, he was probed. He said that a wave of an electron is the electron smudged, like smeared. I don't know how you smear a piece of matter, but that was the best thing he can come up with. Because, again, he had no intentions on explaining it. But remember what I said about Newton, the hypothesis non-fingo attitude. He was like, look, I make no hypothesis. All I can tell you is this is what I see and this is what works. And according to Galileo, which we covered in class 1, if you can prove it experimentally, it's true. You know? So how can a compact atom, the basis of all larger things, including ourselves, breathe spread out waves? Quantum physicists will come to call it the particle wave probability function. And you're going to hear this over and over, probability wave. So the wave is the probability of a piece of matter being somewhere. It's the probability of what? Probability of it being there? Probability of it appearing? Probability of it being here or there? Inspection of the wave mathematically. So again, if you go to the genuses and say, okay, what does the mathematics say? It turns out to be an abstract mathematical. The mathematics show that they could not be real waves. So they're not real waves. Even though we're describing them as waves, there's not really waves of matter, like ripples in a pond. But instead, it formed a complex form of vibrations in an imaginary mathematical space called a configuration space, which, again, means nothing. In this configuration space was all mumbo-jumbo. Okay, so what does it really mean? So to state it simply, a wave is the probability of the particle existing in a particular location in reality. So the wave isn't, there's nothing actually there. It's just the probability of it being there. The problem with probability is we all understand probability, but we understand it incorrectly in the terms of how this goes. Because when we say, what's the probability that I'll win the lottery? It's 1 in 140 million. But the fact is that there really is a probability. Someone will win the lottery. Though an object's waviness may be spread out over a wide region, when one looks at a particular spot, one finds either a whole object or no object. You don't find a spread out portion of an object. So an atom, if you look at a wave of a gold atom, and you finally look at it and you see a gold atom, that wave wasn't the gold atom smudged out. You can't smudge an atom. And here's the best analogy I can come up with, is the shell game. Now the shell game is how we mostly not incorrectly, but this is how we get confused. So if you take a ball and put it under the shells, right, and shuffle them all around, people put down money, and you have to guess which shell it is. And hopefully the guy's so fast that, it's all about how quick you are. Now what's the probability that you'll get it right? 1 out of 3. Okay, let's say 33%, right? Now, if you were to look at all 3 of those shells, I can tell you there's a 33% probability in each of those that the ball will be under there. Now, here's where we go off, is the probability that the ball will be under there, but in all actuality, the ball is actually there, right? So, let's say it's just me and Jeremy. Me and Jeremy go in a separate room, and Jeremy, he gets the bonus round. And he asked me to lift up one of the shells. So I lift up one of the shells just for you, Jeremy. And you don't see anything under it. So what's your probability now? Now you only have 2 shells. 50-50. So Jeremy has a 50% probability. But the rest of us have 33% probability. In the quantum world, it doesn't work like that. As soon as, let's say Jeremy sees the ball, right? You see the ball and I cover it back up. The rest of us still have a 33% probability, right? No. As soon as Jeremy looked at it, there is no more probability. Then it is actually there. Again, I don't know if I'm doing a good job explaining this, so I came up with another one. So let's take a flashlight, right? Imagine a wave of light. We all understand light, flashlight. Now we're going to come up with this is a silvered mirror. So like, your window tint blocks light, right? So this silver mirror will block exactly 50% of the light, all right? So these are good to have on your cars, Most people have it at 80%, like limo dark, So 50% will go through. The other 50% is going to be reflected, Now we have a sensor. That black bar is a sensor. So that sensor, when light hits it, it's going to measure 50%. So if you have 1,000, what's a really bright light? 100 lumens. Those are those really, really bright ones. 100 lumens. That's going to measure what? 50 lumens. Right? Everyone on board with this, right? So we're going to take another silver mirror. Again, half of it will go through. So half of 50% is 25%. So half will go through, and then the other half will go to that bar over there. So that sensor will measure 25%. So now the light's getting dimmer, right? Because now you're at 25% of a really bright flashlight. So you have to, oh, it's not as bright. Half it again, and now you're like at sunglasses, you know. So now we're going to take a mirror. That's the green. Oh, it's going off screen. It doesn't go through that. So I'm going to bounce all 25% over there, all 25% over there. I need space on my slide, people, okay? And then I'm going to have it again. So now the light's getting much dimmer. So this sensor, half of 25 is 12.5%, right? Now you have 12.5% of the light bouncing and hitting the sensor, and the other 12.5% going straight down. And last but not least, let's do it one more time just for giggles, and go down to 6.7.5%. Now this isn't very exciting, okay? This is just light. We all know you can dim stuff, you know. We got dimmers. I got dimmers on my wall, you know. But now imagine this is an atom. So if you were to shoot an atom, and an atom becomes a wave, now you understand that at this point right here, if you were to stop and put the shell over that, it's not that there's a 6.75% chance that the atom will be there. It's a 6.75% chance that the atom will exist once you actually look there. So if this shot atoms, and you shot 1,000 atoms, let's say we shoot 1,000 atoms, 500 of the atoms would end up here. There's a 50% probability. 25% of the atoms would end up here. And then 125 would end up there, and 67.5 would end up there. It's not smudged. So right before you measure it, how do you have 6.75% of this entire gold atom? What, you got like this electron and half of that electron and a piece of the nucleus? So if things were really smudged out, half the atom's there, the other quarter's there is in pieces. As soon as you look, if an atom registers here, you see the whole atom. You don't see a piece of an atom. You see the entire atom. So even if you wanted to think about pieces of it floating all over, as soon as you look, then you would have to imagine all those pieces instantly coming together. The atom like reassembles like a transformer. So that's what we mean about probability. At this point, before you measure it, this is just the probability of it existing, but it has not existed yet. And just like we can do with light, we can do the same thing with atoms. We know that 50% of the atoms will register on that counter. Just the same way we know that 50% of the light is registered because we reflected half of it. The strange thing is that we even have a real-world analogy. Your observation causes the object to collapse into reality. Now, when I say collapse, this is like my terminology, and we'll go over the official terminology in a bit. Meaning you have a wave, and collapse it means there's no wave. So you go from wave to matter, right? We all know matter is a piece of something. A wave is a wavy something. So collapsing a wave is you're going into a little dot. The particle wave is not just the probability of the particle being in an area, but is instead the probability of the particle existing in reality in that area. Now, of course, we have to come to terms with reality, what is real and what is not real, because if something really isn't there, where is it? I mean, non-sci-fi channel, ideas included. For a tossed ball or moving planet, classical physics tells the actual position of a ball or a planet at any time, even when it's not being observed. You can launch a rock from a catapult, and physics can give you with great accuracy the exact location of the ball in its arc at any moment. So when you launch a rocket or you launch, we'll keep it simple, you're going to catapult a rock. Physics calculates and tells you exactly with certainty what is going on with that rock the entire time it's in its trajectory. So you can launch a rock, turn around, and at 5 seconds it's going to be here. It's going to be at this arc. So your assumption is that when you're not looking at the rock, that the rock is still in the air following its trajectory, right? Because mathematically when you look, it's going to be there. Well, this is not the case in quantum. Regardless if you're looking at the rock has an actual position. This is something that they call it counterfactual definitiveness, which is a really fancy way that they say, and if you really break down the two words, it makes sense. Meaning, if you drop a ball, like gravity, and you look away, you know that it's really there because when you look back, it's there. And because no matter how many times you drop something, it's always going to do the same thing over and over. So you are making an assumption. You're making an assumption that just because you're not looking, that it's actually there. According to all these mathematical models and according to the waves, you cannot assume the same thing. Quantum physics, on the other hand, does not tell the probability of where an object is, but rather the probability that if you look, the object will exist, allowing you to observe that object at a particular place. In other words, the object has no actual position before that position is observed. No actual position. Again, I just try to wrap your brain around this. This is really bizarre. 3 different mathematical models prove this exact point. Quantum mechanics predicts the correct outcome for the experiment you actually do. And since correct predictions are all one needs for all practical purposes, there shouldn't be a problem. Remember Galileo said, all experiments need to do is show consistently correct predictions. And that's what quantum mechanics, quantum math, quantum algebra, quantum waves, that's what they show over and over and over and over again. So the science is sound. You can defend this pragmatic attitude using the Copenhagen interpretation, which we'll talk about later. But you have to wonder, how do scientists justify this? Like, how did they come up with this? Because even if this is true, how do you reconcile the fact that, okay, little things aren't really there unless we look at them, but big things are really there? Where's the line in between? You know, how do you coalesce those two ideas? Does nature's fundamental law, the Schrödinger equation, provide only probability? Einstein said, no. There has to be an underlying deterministic explanation for the particular position at which the object was found. Einstein was like, look, just like I think I said it in class 1, just because I'm not looking at the moon doesn't mean it's not there. Which quantum mechanically, that's what they're sort of saying, if you really follow through. No one's looking at the moon, it's not there. Someone's got to always be looking at the moon. If everyone closes their eyes, the moon's not really there. But you open your eyes, and there's the moon, exactly where you thought it'd be. Einstein says, God does not play dice. He's like, this is... And granted, a major issue that the classical physicists and Einstein had was the randomness. Because when you introduce randomness, like I explained earlier, you lose control. Remember, if you can know about everything and where everything is, then you could be like God. You can see the future. You can see forward in time. If you can predict how things are going to happen. But if you can't, if on the most fundamental level it's playing dice, luck of the draw, there's no way you can foresee events to come. Bohr suggested Einstein not tell God how to run the universe. Quantum physics proved that nature was fundamentally random. Truly, truly random. Now, it's funny because randomness, I have to go with my computer analogy because I'm a computer scientist, is that randomness was very, very difficult to achieve for the longest time because true mathematical randomness is like impossible, just coming up with equations. But now they actually have websites, you can Google it, where they will send and stream random numbers. And what they do is they take atoms shooting out stuff randomly according to quantum nature, and they have detectors. And depending on where it hits on the detector, then that gives you a number. So it truly is random. According to the only true randomness is when you get down to the atomic level. Randomness was not Einstein's serious problem in quantum mechanics, despite this much-quoted theological comment. And you'll see this a lot, this comment, if you start doing research, God does not play dice. And most people misunderstand it. Hopefully it makes sense the way I described it, what he was really talking about. What disturbed Einstein and Schrödinger, and more experts today, is quantum mechanics' apparent denial of physical reality. The common term they use is naive realism. Not in the sense of naive like you're naive, but the sense that if I tell you that by not looking at something it's not there, then how do you define what's real? So the whole purpose of real is it's real that it's real that it's real. My wife is at home with my kids. Now, I know that she is home with my kids because I know that they're real and I know they're home. And I can track her location. But if she really wasn't there, then that she was only had a probability of being there. She could be in Prescott at the same time. Then what the heck would reality be like? According to quantum theory, there was not an actual atom in the particular place before we looked and collapsed the wave function and found an atom there. But there are actual atoms and actual things made of atoms, aren't there? In the early 1920s, before the Schrödinger equation, the fact that one could display light and matter either as a spread out wave or as a collection of compact particles was a troubling puzzle. However, here was the hope. The whole hope, ever since 1905, when Einstein did the photoelectric effect, the hope was that some yet-to-be-found fundamental theory might give a reasonable explanation. But by the late 1920s, with the Schrödinger equation, and now Heisenberg's equations, and now Dirac's equations, the fundamental theory seemed in hand, but the fundamental theory was telling you that there was no explanation. That's the easiest way to put it. Once it became clearly apparent that Schrödinger had not resolved the issue of quantum jumps. Remember, the whole reason why he did this is he wanted to get rid of jumps. But after he came out with his equations and people processed it, he realized he did not get rid of jumps. And here's a funny quote. Had I known that we were not going to get rid of these damn quantum jumping, I never would have involved myself in this business. He's like, oh man, that cracks me up. Heisenberg says, the paradoxes of the dualism between wave picture and particle picture were not solved. They were hidden somehow in the mathematical scheme. So without a doubt, the appealing picture of a physically real wave circling around the atomic nuclei that led to Schrödinger to discover the wave equation that now bears his name is wrong. So Schrödinger's equations work, but he was imagining it was a real wave, that electrons really were waving, and that like vibrations in a guitar string that they wrapped around. But now they were understanding mathematically, there really isn't any waves. There's no real wave. Now you can describe it like a wave. It works like a wave when you're not looking, but there's nothing real about it. Wave mechanics is no more a guide to reality of the atomic world than matrix mechanics. But unlike matrix mechanics, wave mechanics gives an illusion of something familiar and comfortable. And this is where we run into the issues is people can understand waves. And even if I tell you, that's why I'm harping on it so much, even if I tell you that these aren't really waves, you just can't help but think, oh, they're waves, And that's another big conception. If you watch any Discovery Learning channel, Nova, they always describe, oh, atoms are probability waves. And your brain says, oh, they're a wave. And then you assume probability. Probability means that they're there. We just kind of know the probability that where they'll be. I'm telling you all that's false. It is an illusion that has disguised the fact that the atomic world is completely different from the everyday world. Note that there is no model of what the atom and the elementary particles are really like, and nothing tells us what goes on when we're not looking. However, the equations of wave mechanics can be used to make predictions on a statistical basis. If we make an observation of a quantum system and get the answer A to our measurements, then the quantum equations will tell us the probability is of getting answer B, or D, or E, if we make the same observation a certain time later. Quantum theory does not say what the atoms are like or what they are doing when we're not looking at them. Now, unfortunately, most physicists who use the wave equations today do not appreciate this, and they pay only lip service to the probabilities. Students now are able to think of the waves are real, and very few physicists nowadays get their degrees with an understanding of what an atom is really like. And I've ran into several people, like one guy had his bachelor's degree in physics, was pursuing his master's, and I'm talking to him about these, and he's looking at me like I'm an idiot. I'm looking at him like he's an idiot, and he's just like, no, it's either way, you just don't understand. I'm like, no, you don't understand. Just like, trust me, Also, students readily accept the notion of probability without understanding what probability really is. Remember, it's natural to say, what is the probability of Jeremy at midnight being asleep? The reality is, either he's going to be asleep or he's not going to be asleep, But regardless, at midnight, something really is happening with Jeremy. He really is asleep or he really isn't, you know? So now we're going to come to the experiment. This is where all this craziness comes from. And I hope you have questions, because it's going to be funny. But do you guys remember when I went over the double slit experiment? I'm going to recap for you, Dom, you know. So if matter acts as a wave, we should be able to test it in the same manner as we do light waves. So, did you see the light wave video? No. Dom, did you see it? Did you see it, Aaron? You know, let me play it just for you guys, because it's hard to explain abstractly, but it's easy to explain if you actually see it.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So,
all right, so does that make more sense? And if you think about a wave in the two-dimensional sense like this, when the top part lines up with the bottom part, they cancel each other out. That's why you had the dark bands. So this is where scientists finally said light is a wave. Because if light was a particle, like Newton said, light in two slits would form two slits of light. But they didn't. They formed an interference pattern. So now let's fast forward to today. We've been talking about all this theoretical nonsense, but it doesn't take a skeptic to know that scientists finally were able to achieve a way where they can actually shoot electrons. So here electrons are the smartest piece of matter, like marbles. So here we have our waves. We already explained that. So what happens now? Oh, I forgot about this. I found this video on YouTube, and it basically shows you the same thing you just saw in that video, but it shows you in real life. I always like real life examples better, but watch this.
They travel out with circular waves.
He's actually using water.
Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern.
And then
This pattern is created by the ripples in the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased.
So those are the dark
constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere, and you wouldn't see any light there.
Yeah, so there's the same thing, but it's real world. I like that, Another thing to note is it didn't really make clear in that video. You always see it, but know that these slits are in lesser intensity, and that's important. So the middle one, let's say that middle one is 100%. The next two would be 80, and then 65, and then 40, and then, it falls off. And again, with the waves, and as they go further out and cancel, they're not as intense. So what do you think is going to happen when we shoot electrons? And electrons are pieces of matter. So electrons, atoms. What do you think is going to happen when we shoot them through the double slits? Or what should happen, according to everything I've been saying this whole class? Huh? Yeah, we should get an interference pattern. That's exactly what we get. So here we're shooting a ball of something, and this is what's so interesting is you shoot it out. So somewhere between when we shot the electron and the holes, the matter became a wave. The wave went through both slits, just like we saw in the water, and interfered with itself. And when it hit it, again, the probability hit the wave all over the place. Obviously, the most probability is what? In the middle. The lower probability, just like my light analogy, think of 50% in the middle and 6.25% at the very end. When it hit, each of those little dots registered not a piece of an atom, not a smudged atom, not a partial atom, electron, but a whole electron. Obviously, electrons are indivisible, but if you were to do this with an atom, which they've done now, you get the same result. So the first thing scientists, even though, remember, the experimentalists, when they did these experiments, and they were still skeptical, because now you're doing real-world applications of theoretical stuff. And the way it goes in the real world is when you test theoretical things, you want to hit it from every angle. You want to make sure you're covering all your bases. So what if, and when they shoot these electrons, they're shooting them like really fast. I mean, millions at a second. So it's possible, remember, it's probable, there's a lot of things in probability, that they're hitting each other, they're interfering. Maybe it's something with the electrons hitting each other that they're forming this pattern. I mean, it's possible. So the easiest way to eliminate that is they're like, you know what, let's redo the experiment and let's shoot one at a time. So we make sure we shoot one, make sure it hits, make sure we register an electron. Shoot another one. So there's no way that these are messing with each other. So they do that. Now at first, they don't see anything. Like obviously there's no clear pattern. But as they shoot more and more, the same pattern emerges. After you shoot, 50,000, the interference pattern emerges. So it has nothing to do with the patterns interfering with each other. Because if you shoot them one at a time, something's going on. So now, if I was an experimentalist, and it's my job to run an experiment to test this, the next question I ask myself is, okay, I shot a particle, right? I ended up with a particle, but the way the particles fell showed me that they somehow became a wave in between. Remember, when we read it on that back plate, we observe it. That's what observing is, right? As soon as we observe it, we collapse the wave. So my first inclination, which was the inclination of scientists, is let's put a measuring device. Let's look. Let's put a sensor on one of the slits, right? So if it goes through, we'll see whether it's a particle or if it's a wave. If it's a wave, we'll see it's a wave. If it's a particle, we'll see it's a particle. And actually, in this particular experiment, you only need to put it at one slit. Because if you shoot an atom or an electron, if you shoot an electron and the sensor doesn't read anything at the top slit, then obviously it went through the bottom slit. So you don't need to have a sensor at both, So they did this because they wanted to see, and they couldn't believe what happened. What happened was this. No more waves. So suddenly the atoms, the electrons, decided to not behave like waves. They behaved exactly how Newton said they behave, just like a particle. So it was the simple act of observing. The fact that we went and observed the electron the electron either went through one hole, or it went through the bottom hole, or mathematically it went through both holes, and it went through no holes. But as soon as we look, then it stands to reason that we collapsed the wave into a particle, and we registered a particle. Now here's what's even crazier, is half of them went through this slit. We're not looking at that slit. So if you fire an electron and it goes this way, we're not even looking here. So you're telling me the electron knew that it was being looked at in somewhere that it wasn't? It was like, whoa, I know you're looking over there, which means you could deduce that I'm coming over here. So I'm going to collapse. How is this even possible? Now, if you think of it in terms of as it's a wave, I always visualize it as like as soon as you touch the wave in any way, it like coalesces, So if you look at it that way, as soon as you touch it, whether it's the top or the bottom, it collapses into reality. But it's still bizarre that it doesn't matter if it goes through the one that's being observed or not observed, you get particle effects. So looking at this, Newton was right. But if you turn off the sensor, Newton was wrong. So here's the next thing scientists are like, okay, obviously the sensor is doing something to the particles, It's disturbing them in some way. Oh, wait a minute. Well, hold on. This isn't right. I think I screwed up my slides. Oh, no, I didn't. Never mind. I'm going to edit that out. I'm tripping, So anyways, the next thing, that's why I left this here, to go back and forth. So if you're not looking at an electron, if you're not trying to see which hole it went through, this is what you get. If you try to look, you get this. You don't look, you look. So the first thing they did is try different ways of looking. Because what if the sensor is interrupting the electron? All different ways, using vibrations, lasers, it doesn't matter, the same thing. If you try to determine which hole it's going through, you get this. If you decide not to look, you get this. The Heisenberg uncertainty principle. And this is where Breaking Bad probably got the Heisenberg. Walter was very uncertain by a lot of things. The Heisenberg uncertainty principle says that the position and momentum of a particle are complementary. They're yin and yang. They're opposite. You can't have one without the other. They're not two separate entities. Or more precisely, the more precisely the position of some particle is determined, the less precisely its momentum can be known, and vice versa. Now, this isn't very weird. Basically means we're dealing with an electron, right? Electron is the smallest particle. They have smaller particles, quarks, but let's say very small. How do we look at something? We look at it with light, right? Light bounces off of it, hits our eyes. That's how we observe stuff. Now, light hitting a bowling ball or a phone, it's not a big deal. But now we're talking about an electron. So think about these little waves. If we were to shoot this wave, like a lower frequency, lower power wave, it would bounce off the electron and give us the speed of the electron, right? We know it was going 55 miles per hour. But we wouldn't really know its position very well, because look how big the wave is. It's like really big, and the electron is really small. In order to know the position, we'd have to use a more intense wave, more energy. This is an electron. Now, we would know its position exactly, but we pushed it. Kind of get what I'm saying? It's like a bowling ball. Like, if you want to measure anything, you could shoot light, sound, it doesn't affect it. But imagine if the only way you can observe a microscopic bowling ball is by throwing another bowling ball at it. Yeah, you could throw the bowling ball and it bounces back, and using that momentum, you could sort of get the speed it was going, but you have no idea what position it was going because you just threw another bowling ball at it. So the very act of you looking at something this small, just with light, literally destroys it. Destroys it in the sense that you changed it. Does that make sense? Questions on that principle? Now, this is what's ironic. This is what really bothered me, like a teleportation. Like, I'm a Trekkie, watched Star Trek my whole life, love Star Trek. And teleportation always just like, dude, it's cool. It makes sense. It's sci-fi, buffer. And I never questioned it scientifically, even though I knew scientists said that was impossible. I was like, oh, you're just saying it's impossible because you don't know how they do it. No, this is why they said it's impossible. If you were to actually scan somebody, right, that means you would have to look at every little atom and its movement where they're at. The act of looking at you, every little piece of you, would destroy you. That's why teleportation before quantum mechanics was impossible. Yes, we could scan you at one instant in time, but just by looking at you, you would scatter. It'd be like the fly. You come out more than wrong. You come out more than splattered. You'd probably just disperse into energy. And what really hit me is when I watched Judge Dredd. Remember the original with Sylvester Stallone? And the bad guy was cloning like an army. And the clones weren't ready in time. And I remember thinking for the first time, this is when I was a teenager, like, wait a minute. In Star Trek, when you beam people, you scan them into the computer. You buffer them. You have people like as a file, and then you like send it somewhere. And I'm thinking, like, if you're a bad guy and you want an army of people, well, why don't you just like keep making copies of them? Like, that's a lot better than making whatever, And this is what made me realize that's impossible. So that's why bad guys can't make copies of people in a teleporter. Now, obviously, we know now teleportation is possible, but it's possible using a crazier aspect, which you haven't covered. But this is kind of it. Now, just to be clear, and if you're watching this online, this isn't really the Heisenberg uncertainty principle. This is how people misunderstand the principle. We'll go into depth later about what it really is. But this is how 90% of people explain the Heisenberg uncertainty principle, is that you can't know the momentum of position because of, if you try to get exactly where it's going, you're not going to know its speed. And if you really want to know its speed, you're going to change its position. A photon doesn't disturb an object like a wall very much, so we don't expect the wall to be affected by looking at it. Electrons are different. Electrons are so small, we have to use electromagnetic energy with a short wavelength in order to see it all. Any amount of this radiation that can be bounced off an electron to be then detected by our experimental apparatus will drastically change the position and momentum of the electron. So that's why we can't know the position or momentum in an experimental sense. So now let's go back to the experiment. Oh, I phased out this picture. Now remember, the sensor is hooked to a computer. The computer tells us if it's going through the top slit or bottom slit. The back plate where we register the electrons is hooked to a computer, and obviously the device that controls the shooting of the electrons is hooked to a computer. So all things being equal, if we're now saying that the fact that we're looking at it with a wave, that we're somehow changing its course. Now, of course, that's ridiculous, because how do you change the course exactly to line up if it went through both slits? Or how do you change its course just exactly where it makes an interference pattern? It doesn't make any sense. But rather than going through all crazy mathematics, you're like, you know what? Let's unplug it. Now, when I say unplug the sensor, I mean the sensor's still doing whatever it's doing. Shooting waves of energy, doing whatever. The only difference now is what? We can't read the results. Like, we unplug the cable to give us results. So we cannot know what's going on with the slits. So what do you think happens? The interference pattern comes back. So it's not the fact that we're disturbing it using some type of measuring device. It's the fact that we are trying to measure it. Like, we're consciously made an approach to try to measure something, that the interference comes. And if we're not consciously trying to look for it, then the wave continues, and when it hits the wall, the wave probability hits, and we get the interference pattern. So now scientists are like, what the? And the pseudoscientists have really gone a lot further with this. Regular scientists stopped here, but pseudoscientists, because the whole point is, how do you trick the wave? Like, if consciousness really defines reality, meaning the wave collapses into an electron if you consciously try to look at it, then can you trick that? Can you trick science? They've done things where they accepted the data into the computer, but they accepted it in an encrypted format that nobody knew the password to. You get interference. And then maybe they took 3 people, and maybe one person knew the password, but the other 3 didn't, and they recorded things. So now you're recording measurements it's encrypted. But now the difference is someone can actually go back and decrypt it and know if it was a particle or a wave. So the wave knows. It does exactly what it should every time. There's no tricking it. There's no, this is actually the real power behind quantum radar. Now, quantum radar is revolutionary in a whole bunch of aspects, but this is why. If you're a Apache helicopter and you're quantumly cloaked, yes, you have really good cloaking. But the fact of the matter is according to these same principles, you know with certainty whether somebody saw you or not. Now, the whole thing with stealth is you got to go in there quietly. The Navy SEALs, the element of surprise. If you were ever discovered accidentally and you're going into an ambush, you have no way of knowing. Here, you know. You know with certainty. There's no tricking it. Because the pilot knows that I'm still looking like a wave. If I'm looking like a wave, nobody has seen me. So there could be some guy on a radar screen in China as you're going to invade, and he sees a blip on the screen that could be you, And he's like, oh, no, that's not a plane. You're still a wave. Well, let's say 5 minutes later he goes to a supervisor. He's like, dude, I saw something on the screen, and I think it could be something. Supervisor goes and checks, and he's like, whoa, and then he identifies that as a plane. Bam. Instantaneously, because you are now you know that you have been discovered because you're no longer a wave, you're a particle. Now that's some trippiness, It's not it almost seems sort of telekinesis, not telekinesis, but telepathic. Now you're not reading people's minds. You just know using these principles, and we'll go over later how they actually act these out. But you can know in principle whether you've been observed or not. It's all about observation. Observe. Oh, apparently I zoomed in. Now here's the video, the rest of the video, might as well.
All right. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. And we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both.
So that helped explain it better than I did, And again, over and over as technology progresses, they continually keep running the same experiment. That's why I said this experiment. Now I'm going to go over some really, really other cool experiments, but everything runs back to this experiment because all the mysteries are contained there. Like, how does consciousness tie into things becoming real? This next experiment they performed, and I didn't have time to make slides. I just grabbed these off some website. I don't know where I got them. But this was an experiment that they couldn't run until the late 80s, and you'll see why in a second. So what they did was this. So they had the double slits, and they had two sensors instead of one, and they moved the sensors back, and they put a film. So they put a wall, right? That wall up. Now this wall is electronically controlled. So this film can be pulled away or put back. So the goal is we're going to try to trick. Because if we look here, we collapse the wave into a particle. If we wait for it to hit the sensor, it collapses into a particle. So what if we let it go through the slits? So if it goes through the slits, it's a wave. But before the wave hits the sensor, we remove the film and look. We should see waves. So they let the particle wave go through the slits unobserved. Being unobserved, the particle wave remains in a state of quantum superposition as a wave. That's what it's called, quantum superposition. It's in all positions all over the place. So it's a wave. Now the wave is still traveling at the speed of light. That's why they need really fast electronics to even do this in spaces. This isn't something you could do in the 1920s. Now they're going to remove the wall. So now there's still space. Okay, there's space between the cameras and the waves. The waves haven't hit anything, but we're looking at them. So what do you think happens? Anyone? Yes, they collapse into, oh, I didn't put the slide in there. Basically, they collapse into just like we see it. So there, again, there's no tricking it. Now, the thing is that if these really are waves, which I've hoped to convince you that they aren't really waves, if they really are waves, so imagine that Schrödinger was right, these are real waves. Then as soon as we ran this experiment, if they were real waves, that would mean that they would have to, the cameras must have sent a superluminal signal to them from the future, you know? Because we're looking, and if they're real waves, then the electron, then we would have to, a signal would have to be sent from the past to say, hey, he's going to look. So look through the slits. I mean, go as a particle. So now you should go as a wave. Obviously, that's not possible. You can't go faster than light. But of course, there's ways around that as well. And again, it's using these types of principles. So in other words, these are not real waves. The fact that they're modeled and behave like real waves is another trippy phenomenon, but they are not real waves. They do not exist in reality. The fact that they exhibit mathematical similarities to real-life waves, do not be deceived. So now if we go back to the Heisenberg uncertainty principle, of course I misled you when I explained it the first time. My reasoning is that this sadly is how the principle is commonly understood by most people. And people online in those message threads just drive me nuts. The effect I described earlier with the flashlight is simply the observer effect, in which the act of observing of something, you can ultimately change it. So that whole analogy I gave you, that's not the Heisenberg uncertainty principle. It's actually called the observer effect, which is the same thing. It just means when you get down to the small enough stuff, by you observing it, you have to observe it how? Using little pieces of either, if you think of light as a particle, as a photon, you could see you run into issues. Because you're taking one bowling ball and throwing it against another bowling ball and wondering why you can't tell which direction the bowling ball was originally going in. Because you just knocked it, you know. Or if you think about it as a wave, as soon as you get enough energy to know what direction it's going in, you change the direction. That's the observer effect. Very similar to the Heisenberg uncertainty principle. Understand the Heisenberg uncertainty principle is the central pillar of quantum mechanics. So it's important to understand it. That's why I'm harping on it, because we'll always come back to this. And so many people misunderstand it, and it throws them off. Ideas like position or velocity or spin, which we'll get into later, simply don't have the same meaning as in the real world. In a visit Schrödinger had with Bohr and Heisenberg, Heisenberg found that the two of them were at odds due to conflicting understanding of concepts. Basically, they were arguing about a whole bunch of stuff, and Heisenberg's there too, because, you know, him and Bohr are like buddies. And he's realizing, look, you guys are not arguing about the right things. You're arguing about a difference in ideology. And that's where he actually formulated the Heisenberg uncertainty principle. By looking at his own work, he was able to show, like, okay, this is how we need to think of it. Heisenberg thus came up with the principle to bring clarification to the matter. Though it seems obvious to him, it apparently wasn't obvious to everyone else. He went back to the equation, PQ minus QP equals H over I, which translates to the change in X. Basically, your change in position multiplied by your change in momentum is equal to Planck's constant. No, sorry. It has to be greater than or equal to Planck's constant divided by 2. This is essentially a very mathematical way of saying what I said before. The closer and closer you get to the smallest unit of measure, the more wavy things become. Heisenberg came up with the principle to bring clarification to the matter. Though it seems obvious to him, it apparently wasn't obvious to everybody else. He went back to the equation QP minus QP equals H over I, or the change in X. Did I go to the same slide? So the more accurately we measure the position of a particle, the less accurately we know its momentum, and vice versa. Many experimenters misunderstood this and took this as a challenge to their skills. So experimental physicists, they were like, well, what are you trying to say? That I can't build an experiment good enough to know the position? Because if you tell someone, you know, if I tell LeBron James that you cannot hit a free throw while jumping backwards doing the flip, not basically challenging his skills, you know, and an athlete or someone's going to be like, no, I'm gonna work at it till I can do it. I'm going to try to achieve this. That wasn't what he was saying. They imagined he was saying that their experiments wouldn't be good enough to measure both position and momentum at the same time. This misconception still comes up all the time. Heisenberg himself used the idea of observing an electron to make the same point. Now, this is all great and true, and it gives a casual person a general understanding of the position, but it's still far from the truth. What the uncertainty principle tells us is that there is no such thing as both a precise momentum and a precise position. In the heart of the matter, there's no such thing of having a precise position and a precise momentum. Now, this all goes to how we say it. Like, if you were to say something has a precise position, then it does not have a precise momentum. If you were to say something has a precise momentum, it has no position. So how could something be something and not have a position? A position where? Here, in reality, in this whatever. He says, we cannot know as a matter of principle the present and all its details. Remember, to know the future, the thing is, nothing in quantum mechanics prevents you from knowing the past, which we understand perfectly. Once it happens, you know it, you can know with certainty what happened. But you can't look forward into the future, which really irritated a lot of the old school. This is where quantum theory cuts free from the determinacy of classical physics. To Newton, Isaac Newton would tell you right now, it would be possible to predict the entire course of the future if you knew the position and momentum of every particle in the universe. It's kind of like where I went in class 1, like the Tower of Babel. You know, if all the people got together and if they really knew enough, if they had enough knowledge, way beyond building a tower, and way beyond reading all the books, if they knew where everything was going at every moment in time, you could know everything. You could be like God, so to speak. But to a modern physicist, such perfect prediction is meaningless because we know the Heisenberg uncertainty principle means you cannot know the position and momentum of even one particle. Now, when I say cannot, again, don't be confused as in it's a limitation in your skills, you know? When I say you cannot is you don't have. It's one or the other. It's yin and it's yang, all right? It's like, does that make sense? Because if this doesn't make sense and going forward, you start getting more and more confused. The same conclusion comes out of wave mechanics, Born matrices, and Dirac's Q numbers. So all three mathematical principles can formulate the Heisenberg uncertainty principle in the same way. Meanwhile, although the uncertainty relations had been derived from the fundamental equations of quantum mechanics, some influential experts begin to teach quantum theory by starting out from the uncertainty relations. Wolfgang Pauli, which we skipped over him, he was another super genius physicist. He wrote a major encyclopedia article. Remember, people, before Google came, there were encyclopedias, okay? Yeah. And there weren't a lot. So if you wrote an article in Britannica Encyclopedia, like that was it. Like that was the Google link, you know? All the libraries had that. So the fact that he got to write that, obviously it's a major privilege, and he deserved it. But if you wrote it wrong, if you wrote it incorrectly, if something in encyclopedia was blatantly a lie, it'd be hard to know. Because, hey, do your research. I did my research. Research was wrong, you know. He encouraged a colleague to begin the college. So anyways, he wrote his quantum article, but he started with the uncertainty principle. And his colleague, who was really close to him, wrote the major textbook that would be taught in all the colleges, started from the same thing. Now, you should be able to grasp how this can hurt somebody if you start from the uncertainty principle instead of starting from the real mathematics that led up to the uncertainty principle. Students raised on these texts, students who later become professors, in their turn, still introduce quantum theory with the uncertainty relations. This is a peculiar accident in history, since if you start with the uncertainty relations, there's no way to work out the basic quantum equations. What's worse is that the only way to introduce uncertainty without equations is to use the examples like photons hitting electrons. So imagine you're a quantum, and again, I've met people who this is their major, and they're far more smarter than me as far as mathematics and that type of stuff. They could run circles around me. But the fact that they were taught incorrectly, in my opinion, they were way off course because they were taught the uncertainty principle first. So first you get a false notion that you understand about, oh, that makes sense. Like if you look, you know, yeah. Of course, you're misunderstanding uncertainty. Uncertainty really means that there is no real position or whatever. And then you follow through with a wave, and they're taught waves. They're not taught Dirac's and Heisenberg. So now they're thinking atoms really are waves. They're like waves, and they can imagine them going around an atom. They can imagine waves. And you can imagine why they don't grasp the real deepness of what's really going on. You know, if you talk to a physicist about reality and this and that and determining, they'll look at you like, no, you don't know what you're talking about. You know, it's all about the probability wave. You know, well, what is the probability wave? The probability of what? And sadly, a lot of them won't be able to answer you. This immediately makes people think that the uncertainty principle is all about experimental limitations, not a fundamental truth about the nature of the universe. You have to learn one thing, and then you have to backtrack something else, and then you have to move forward to discover just what it is you learned in the first place. Here's the overall result. It's generations of confused students with misconceptions about the uncertainty principle. Misconceptions you don't share, you guys, because I taught you the correct way. So I hope at the end of this class, you understand, because 9 out of 10 people, if you're at Starbucks and you happen to mention the uncertainty principle, they're going to give you the other principle. You know, oh, it's because you can't know because experimentally. You know, and if you look at them and say, actually, no, that's not really it. Things really don't have a position. No, if something has position, it really doesn't have momentum. And if it really has momentum, it doesn't have position. They're going to look at you cross-eyed. You know. And that's really where I want to leave off. The Copen. Any questions? You got to have some questions. Like, how would you, if you were running this experiment, what else would you do to try to prove that consciousness wasn't really affecting it? Like, how could you trick it? No? Ron? Brandon?
Is there a way to do an experiment that doesn't have an electronic way of monitoring?
Ah, yes.
Like maybe just pick some kind of
Like if it goes through the paper, like makes a little hole?
It went through some kind of special paper. But if you read it, you see what I'm saying? Then
Yes, and
electronic because
they've done
possibly
something
some
similar
kind
to
of
that.
electronic would maybe interfere.
They've done something similar to that. And again, no matter what they do, it's the same thing. A really famous one is they use light, very light. And they use some type of amplifier. So you could see that if the electron went through as a particle, you would see like, you know, like in a fog, and you see like a little, like a tracer. You know, like a bullet tracer? You would see the tracer. And you could see the tracers if you were looking. But then if you weren't looking, or if you looked less, because you can't not look, but the less and less you look, the more like, imagine you're looking at it through a piece of glass. Gosh, it gets really that's why this is the next thing we're going to cover in next class, is cover the Copenhagen interpretation. And that is, how do scientists grapple with this? You know, before we even go, because Einstein's going to attack this head on, you know, but because basically they're saying, this is basically what scientists say. Scientists say, look, the little stuff is all wavy, right? The big stuff isn't wavy. But you can't see, I can't see the atoms of wood, right? So, basically I shouldn't be concerned with it. Like you basically dismiss one thing away from the other thing. Which sounds like a cop-out, but that's basically what they do, you know. Now Einstein wasn't willing to accept that. Einstein was like, no. You know. Here, I'll give you a glimpse, because we still have 10 minutes here. Einstein attacked, he had to formulate an attack on quantum mechanics, right? And it actually wasn't that hard. Well, it's easy when someone figures it out, how it's not that hard. The heart, and that's why I harped on Heisenberg uncertainty principle. The heart of quantum mechanics is the uncertainty principle. That's why you get all this weirdness. Because as soon as you observe something, as soon as you know its position, it has no momentum. It has no wave. You know, so it's kind of a way to mathematically think about it. So Einstein attacked the uncertainty principle in this sense. Is he imagined this theoretical, imagine two trains separated by a very, very powerful spring, all right? As soon as the spring's clamped down. As soon as you let go of the spring, it's going to fling the trains away from each other at near the speed of light. Okay, it's a frictionless train track. You know? Now, just that basic principle. If you need to remember the basic, you have two trains going in opposite direction at 50 miles per hour. So Einstein's like, look, if you were to do that, and they've actually done this. They've actually, in the late 80s, they actually found, because Einstein, it was a thought experiment. They actually made it a real experiment, which they tested. But here's how it goes. So imagine there are two particles, two electrons, and you manage to shoot the two electrons away from each other at the speed of light in opposite directions, right? Now, the basic word problem is, in 4 seconds, right? The Heisenberg uncertainty principle says you cannot know with certainty the position, the momentum, right? So they're going apart from each other. I'm over here. I'm looking at the one going this way, right? And I observe it full on using whatever methods, and I know its position. I know it's 1 mile away from the starting point. Do you see the... So by deductive reasoning, it's like, aha, if I know its position, you're right, then I know exactly its momentum. Because it went 1 mile in 1 second, it's going 1 mile per second. So that other particle is still a wave. I haven't observed it. But when I do observe it, I will know its momentum before I observe it. Therefore, quantum mechanics, now he couldn't say it was wrong, because it's not wrong. Every prediction of quantum mechanics using these equations works. Einstein says it is incomplete. You are missing something. And Einstein called it the hidden variables theorem. He was like, you're missing something. Basically, he's like, there's hidden variables. There's some other way of looking at this where there's a mechanism that will explain it, because just using that basic principle, Einstein thought he had it in the bag. And even if you really think about it, how do you prove that wrong? If you know this train is going 100 miles per hour, and I measure the train, I know it's going exactly 100 miles per hour. If you know where the train started and you know its speed, you know exactly where it's going to be every second, right? So the other train is a wave, according to quantum physics. According to quantum mechanics, if you haven't observed it, it's not there in reality. It does not have a position or momentum. But you know it before you see it. Now, in doing that, and once they did that, it became more like, when Einstein really came, he had these intellectual battles with Bohr, and they went at it. But in the end, everyone's just started to ignore them. Because it's like, look, first of all, this works. And I don't know if you know anything about this. If you're a doctor, you're a physicist, that's your job, right? How do you make money? You need to publish papers, and you need to produce stuff, So if you grab these equations, and you're now making breakthroughs, and you're advancing in science, you don't care about how it happened, The other analogy, the simple analogy is the one they used on the Nova channel was the gloves. So imagine you have two briefcases, right? And in one briefcase you put the left-hand glove, and the other briefcase you put a right-hand glove. And you take those two briefcases and you separate them. Put one in China, one in New York, right? According to quantum theory, in each briefcase there's just a wave, a probability of a right and left glove, right? As soon as I open my suitcase in New York, what do I see? A right or left-hand glove, right? So if I see a left-hand glove, I know that the suitcase in China will have the opposite. So if I have a right-hand glove in New York, the one in China will have a left-hand glove. Always. Now, Bohr would say, no, it doesn't work that way, And he came up with some crazy whatever around it. But in the end, it ended up, here's what Bohr said. I'm just giving you too many freebies, I just can't help myself. Bohr said, as soon as you looked at the right-hand glove, you influenced the glove in China to become left-handed. That's literally the word he used. You influenced it. Now, faster than the speed of light, instantaneously you influenced it. Einstein's like, really? No, if you see a left-hand glove, it was a right-hand glove. The whole time, before you open the suitcase, Einstein's like, there's something real. There really is a glove in this box. There really is a glove in this suitcase. Sorry. Bohr was like, no, they're just potential. Einstein said, as soon as you look, you see a glove because you see a right-hand glove because there was a right-hand glove. And when they open it in China, they see a left-hand glove because there was a left-hand glove. Bohr and the quantum physicists were like, no, Before you opened it, there was both a right and left-hand glove at the same time, just like the alive and dead cat, at the same time. As soon as you looked, you randomly, quantum mechanically, collapsed that left or right into reality and saw a left glove. You not only did that, but as soon as you simultaneously collapsed that, you also collapsed the other glove in China. Now think of it from a scientist's perspective. What are you saying? You're not saying anything. No matter what, at the end of the day, you're going to open one and see a left, you're going to open one and see a right. Who cares what was there before you saw it? I mean, that's really the heart of the matter. That's why it became philosophical. And actually, it was forgotten about for like 50 years, because nobody could prove it. And that's why Einstein's paper on this is the most cited paper from before 1950, the early 20th century, than any other paper. It's actually the only paper quoted, because nothing else is really relevant pre-1950 because we sort of advanced. But all these ideas Einstein comes up with that. So as you can imagine, that's where we get, how many of you heard of quantum superposition before I said it here? Quantum superposition states exactly what Bohr states, that if you can accept that a particle could be a wave outside of reality, that's hard enough. The fact of the matter is that particles can not only be waves, but they can be connected to other wave particles outside of reality. So that what you do with one will instantaneously affect the other one. The easiest analogy is if you had a tennis ball in a safe in San Francisco and another tennis ball in a safe on a pedestal in China. If you knock the tennis ball down in San Francisco, simultaneously the tennis ball will knock down in China. They're connected to each other, outside of reality. Now Bohr called it influences. But again, these are real. This is how you start getting into teleportation and to getting into all these crazy things, that things are connected outside of reality. Whether their waves get tangled together, So when you did look at the left or right, the cat alive and dead, as soon as you saw that it was left, you instantaneously made the other one right. And this is faster than light. Like they've actually, the most up-to-date experiment was like in 2012, and I believe they were somewhere in Texas, like Dallas. And then the other group was in Europe. No, they weren't in Europe. They had to be continental. We couldn't cross because we needed the fastest electronics available. And they measured doing this exact thing, how fast that signal got sent. Now, according to quantum mechanics, it's instantaneous. But we can only measure it according to what our speeds are. And so far, they've measured it at 10,000 times the speed of light. That's only because that's the fastest of the most modern day instrumentation that can even calculate these things. But again, you can't go faster than the speed of light. But outside of reality, turns out you can do whatever you want. So that concludes. I hope you enjoyed learning about the experiment. What? Yeah, it's just like yin and yang. One thing or another. And again, next week I'm going to cover some really cool experiments because again, the name of the game is try to trick the wave. That's really what it's all about, if you think about it as a game. Now that they know that things can be entangled, it's called quantum entanglement, that you can connect two things so that when you look at one thing, it makes another thing appear. They're going to use those properties to, again, try to challenge the wave, Scientists are doing every which way to prove that this isn't true. Not that they don't believe it's true, but they're constantly finding out ways to do that, This is the heart of quantum encryption and all of this, And then I already explained I didn't really explain it, but I gave you a glimpse of quantum cloaking devices, Like, yes, quantum is going to be state-of-the-art, and the only way to observe a quantumly cloaked ship, or by that point we'll be at ships, spacecraft, were to have another quantum device. But even if you did, militarily, knowing with certainty that you have been observed is beyond a tactical edge, Because if you're a Navy SEAL and you're going in and you're just about to land and you're like, oh, we've been seen, what are you going to do? You're going to turn around. We have been seen, You can mathematically achieve the element of surprise. But I'll stop. Until next time. Any questions? No questions?